Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 7th episode of my tutorial series on Z80 assembly language development, targeting the Sinclair ZX Spectrum to learn how to program a simple system starting at the very lowest level. If you haven't seen the first episode, I strongly encourage you to go back to my channel, and don't forget to subscribe and click the bell to be notified when the next episode comes out, and start this playlist from the beginning. So far in this series, we have learned the basics of assembly language and went over how to deal with data in whole bytes and words, moving it around and doing simple arithmetic. However, the Z80 has many instructions that deal with data on the bit level, where you can do logical operations, shifting, testing, and simply setting individual bit states. There's a lot to go over here, so let's get right into it. To review, a bit is nothing more than a single binary state, true or false, high or low, 1 or 0. Bits are the basis of digital computing, as there is no in-between value, which makes things simple on a basic logical level. A byte is 8 bits, and the mnemonics of Z80 assembly language, they are numbered 0 to 7, with 0 being the lowest bit at the rightmost position. Bit 7 is the highest bit at the far left end, which is also used as a sign for 8-bit values. With 8 bits, a byte can have 2 to the 8th power different values, which works out to 256, with a range of 0 to 255. But for the purposes of this lesson, we don't care about the numerical value of the byte, only the values of each bit. Now, let's see how we can deal with them individually. As bits are effectively true or false values, computers essentially just perform logical operations on them, using the laws formulated by the 19th century British mathematician George Boole. He is the namesake of Boolean logic, where we can break down any mathematical or logical operation into a sequence of simple operations. The most simple is the NOT operation, indicated by a tilde, where the result is the opposite of a Boolean value. So if the value of A is true, then not A is false, and vice versa. For digital logic, we use 0 for false and 1 for true, and we can see how the NOT operation works in this truth table. The other operations are binary rather than unary, meaning they are the result of 2 input values instead of 1. The OR operation, indicated by a V, will result in a true value if one of the input values are true. So A or B will be true unless both A and B are false. The AND operation, indicated by an upside-down V, will have a false result when at least one of the inputs are false. So A and B will be true if and only if both A and B are true. The last basic operation is called exclusive OR, which is indicated by a circle with a cross inside it. The result of A XOR B will only be true when A and B have opposite values, so the result will be false if they are both the same. These 4 operations are the basis of all digital logic, and every operation we have seen with the Z80 is derived from combinations of them, as implemented by electronic gates in the microprocessor. But this series isn't about hardware, just software. And the Z80 instruction set lets you do all of these operations on data in registers and memory. We'll start with NOT, which is done with the CPL, or complement instruction. This simply performs a NOT operation on each bit in the accumulator. So each of the 8 bits is flipped to its opposite value, and that's it. The Z80 doesn't let you do this with any other register or memory location. So if you need to invert a whole byte like this, you need to load it into A first, do a CPL, then load it back to where it needs to be. The only side effect of CPL are that both the N and H bits will be set. The OR instruction will perform an OR operation between the value in the accumulator and another 8-bit value from either a register or memory. The result is then stored back in A, but the other value is unaffected. OR has just a single argument, which can be any of the general-purpose 8-bit registers, including A itself. And OR A won't change the value in A, but it does have the effect of clearing the carry bit, so you will often see it used for that purpose. You can OR with a value in memory by placing its address in HL and using register indirect addressing. Or you can use an offset from an address in one of the index registers. Finally, you can do an OR with an immediate value so that it is only in the code. This is generally used to set certain bits in A by having only those bits set in the immediate value. We've seen this before when converting decimal numbers to number character codes, which you can do with an OR hex 30, which will set the necessary bits for the conversion. Beyond the carry bit getting cleared, the rest of the system flags are affected too, including the N and H bits, which will always be cleared, just like C. The PV flag is used in this case for parity with the resulting value in A. The other flags are modified as expected, with S being set to whatever ended up in bit 7 of A, and Z is set if A is now all zeros, meaning that A was 0 before, and whatever value it was ORed with was 0 as well. It's this Z-bit behavior that lets us use the OR instruction as a holistic OR that we would see in high-level languages, and not just a bitwise operation. The AND instruction works much like the OR instruction, except that it does a bitwise AND for each bit in the accumulator and another 8-bit value. AND supports the same arguments as OR, including AND A, which will also leave A unaffected and clear the carry bit. In fact, AND A and OR A have completely identical results, but for some reason, OR A is more commonly used. Otherwise, AND is mainly used to clear a set of bits in the accumulator, often with an immediate bit mask. Each bit that is clear in the value will be cleared in A, while the set bits are unaffected. A good example is again with decimal numbers, except we can use an AND 0F to clear out the upper nibble and just get the value of the decimal digit represented by a numerical character code. All the flag results for AND are the same as they are with OR, which means that again we can use the Z bit for a holistic AND. If A is non-zero and it is ANDed with another value with at least one of the same bits set, then the Z bit will be clear. If A started out with 0, then no matter what you AND it with, it will stay 0 and the Z bit will be set. The XOR instruction does an exclusive OR, again with A and an operand, and the result is stored in A. Yet again, all the same arguments are available, and the flag results are the same. But this time, if you do an XOR A, it is guaranteed to make A 0. This turns out to be a great shortcut for loading 0 into A, as long as you don't mind the carry bit being cleared too. A good use for XOR is for flipping bits in the accumulator, which will happen for every bit that is set in the operand. Doing an XOR hex FF will have the same effect as CPL, whereas an XOR 0 will preserve the value in A while setting all the flags based on that value. But there's no need to do that when an OR A will effectively do the same thing, but much more efficiently. Another bit operation we have already seen is shifting, which comes in handy for fast multiplication or division by powers of 2. But there are many other cases where we want to move bits around in lockstep. Bitwise shift instructions on the Z80 only operate on a single byte at a time, which means that when the bits are shifted to the left or right, the other end needs to be filled in with a new bit value. The Z80 gives you many options for determining this value, which could always be 0 or 1, or come from the carry bit, or from the current register value. And then, to shift more than 8 bits will require you to string together multiple shift instructions, as we will see soon. We have used SLA, or shift-left arithmetic, before to do multiplication by 2. It does this by shifting the bits in a register or memory location to the left and filling bit 0 with a clear bit. It also sets the carry bit to the previous value of bit 7, which is now shifted right out of that byte. The Z80 lets you perform an SLA on any general-purpose 8-bit register, as well as memory locations specified by register indirect or indexed addressing. A shift-right arithmetic, or SRA, will do an effective divide by 2 by shifting the bits in the register or memory location to the right. Sign is maintained by preserving the state of bit 7, so negative numbers will be filled with 1s and positive numbers are filled with 0s. The previous state of bit 0 is shifted off into the carry bit. You can use SRA on all the same registers and memory addressing modes as SLA, but if you want a way to shift left while filling with 0s like you do with SLA, then you need a different instruction. That would be shift right logical, or SRL. This works the same as SRA, but always fills with 0s rather than preserving the sign bit. Again, it has all the same available addressing as SLA or SRA, and like SRA, the old bit 0 is shifted into the carry bit. While it's not documented by Zilog, there is a shift left logical as well, and most assemblers support it. It goes by different mnemonics, SLL or SL1, because it fills with ones every time. It's not quite as useful, which may explain why it's not documented, but it is still taking up space in the opcode table. For SJASM Plus, you can use either the SLL or SL1 mnemonic, and use any of the operands that are available for the other shift instructions. And like SLA, it will shift the old bit 7 into the carry bit. The Z80 also has various rotate instructions, which is why all of those shift instructions shifted their leftover bits into the carry bit. The rotate instructions will take this carry bit as an input, as well as the original value, and this lets us string together a shift and some rotates to do a shift across multiple bytes. A rotate will take in the carry bit and shift out a new bit into carry for the next instruction. The rotate right, or RR instruction, will shift the register or memory value to the right, filling in bit 7 with the state of the carry bit, and then setting the carry bit with the value's previous bit 0. So if you had a signed 16-bit value in BC, you could do an SRAB followed by an RRC, and that would effectively divide that value by 2, with a remainder left in the carry bit. RR can use any of the addressing modes of the shift instructions, but instead of using A for an argument, you can use the RRA implicit instruction, which actually does the same thing but faster. The only difference is that RRA will always preserve the S and Z bits, while an RR space A will set S if the new value in A is negative, or it will set Z if the new value is 0. Rotate left, or RL, works the same way, but shifting to the left. The new bit 0 comes from the carry bit, which will be replaced with the old bit 7. You can use this for 16-bit multiplication. The value in BC will be multiplied by 2 if you follow an SLAC with an RLB. Note that shifting to the left requires you to start with the low byte instead of the high byte, but you still want to start with a shift left instruction, and then do a set of RLs until the whole value is shifted. There is also an RLA instruction, which is a faster version of RL space A, and like RRA, it will preserve the S and Z bits. The RRC instructions work similarly to RR, except that it doesn't use the carry bit as an input. Bit 0 is still shifted out to the carry, but it is also copied to bit 7, so it does a complete rotation within the 8 bits of the specified register or memory location. This may seem like more of a proper bitwise rotation, but it is used less often than the RR as it breaks the ability to do division. There is also an RRCA instruction, which like RRA is a faster version of RRC space A that preserves the S and Z bits. RLC does an internal leftward rotation, just like RRC, but in the opposite direction. At the end, bit 0 and the carry bit will match, containing the old state of bit 7. Because of this, it can't be used for multiplication like RL can. And again, we have a shortcut for the accumulator, with RLC-A being a faster version of RLC space A that preserves S and Z. While not strictly bitwise, there is another pair of rotation instructions, and they're used specifically for binary coded decimal numbers, or BCD. These are RLD and RRD, and we'll get into the intended use of those in another lesson. For now, just note that these do not operate on single registers, but on both the accumulator and a memory location whose address is in HL. Also, they rotate 4 bits at a time, which is what you need to represent a decimal digit. Here we are treating A and that memory location as a virtual 12-bit register, with the lower nibble of A being bits 11 through 8, while bits 7 through 0 are simply the byte in memory. An RLD will do a leftward rotation of these 3 nibbles, with the upper nibble in memory going to the lower nibble of A, the lower nibble in memory shifting up to its upper nibble, and the lower nibble of A now going to the lower nibble of memory. The upper nibble of A is unaffected. For RRD, it simply goes in the opposite direction, with the lower nibble of A shifting into the upper nibble of memory. The former upper nibble of memory is shifted to its lower nibble, and finally, the former lower nibble of memory shifting into the lower nibble of A. Again, the upper nibble of A is unaffected. For both of these instructions, the carry bit is preserved, unlike the other kinds of rotation. We first saw how bit addressing works back in Lesson 2, but now we'll go deeper into how those instructions work. Bit, RES, and set all take a bit number for their first argument. Then the byte in question is referenced by the second argument, where it can be specified as an 8-bit register or a memory location whose address is in HL or at a specified offset from an index register. The bit instruction simply tests a specified bit and sets the Z bit if it's clear, or clears Z if it's set. That may seem a bit counterintuitive, but it makes more sense in the assembly code. You would follow a bit instruction with a conditional instruction, using the NZ or non-zero condition when you want to do something when the bit is set. A Z condition would be when the bit in question is 0. Bit can have any bit number, 0 through 7 for the first argument, and the second can be any general-purpose 8-bit register, using HL indirectly or an offset from either index register. Bit will not change the register or memory location being tested. It only affects the Z flag as expected, as well as clearing the N bit and setting the H bit. The carry bit is preserved, but the other status flags will be set to unknown states. The reset instruction, or RES, has the same arguments as bit, but instead of testing that bit, it forces it to be 0. In other words, it resets the bit. Unlike the bit instruction, RES preserves the state of all the flags, even if the bit that was cleared caused a sign change or was the last set bit and the affected byte is now 0. If you don't care about preserving the flag state, using the AND instruction will usually be faster if you just want to clear a set of bits in the accumulator. The set instruction will set the specified bit, effectively doing the opposite of an RES instruction with the same arguments. Like RES, set will preserve all flag states, but will also usually be slower than just using an OR instruction when you want to set bits in the accumulator. Now let's see these instructions in action. The simplest way to do that is to simply perform some operations on registers in memory, and then print the results in binary to see how they work on a bit level. On the Spectrum, we can use color coding to make it easier to pick out which bits are for which value. So let's go to the code. We'll start with a standard device definition and jumping to the start of code. Then we define some addresses for ROM routines that we need to call to clear the screen and print a string. For data, we have a string that we'll use for a screen header. For each line under the header, the first 8 characters will be the bits of the accumulator, followed by the bits of registers B and C, then the byte in memory at the address in HL. Now we need to actually set aside that byte in memory, and we label that HL var and give it an initial value of 0. With all our data defined, we move on to our code after the start label. The first thing we do is to make it possible to return to BASIC cleanly by preserving the alternate HL register on the stack. Now we can get down to doing our actual program. First, we clear the screen using the ROM routine, then load up the header string address and length into the DE and BC registers, and call the print routine. Our header will now be on the screen, so let's start printing some values. We first set up A, B, and C with some arbitrary values, and HL with the address to the HL var byte we defined earlier. Then we write a new arbitrary value to that byte, and we have all 4 values initialized. To print them out, we call the binregs routine, which we'll define later. The first manipulation we do is to do 2 RRCA instructions, which will rotate the bits in A 2 places to the right, with the rightmost 2 bits in the original value shifting to the left end, as illustrated in these comments. We call binregs again to print the new value on another line. Next we do an SLL on A. Since bit 7 of A was set, this shift will set the carry bit and fill bit 0 with a 1. The following SLAA will shift A to the left again, this time clearing the carry bit and filling bit 0 with a 0. Another call to binreg should print a line with the final value of A as predicted in the comments. Now we are going to shift everything to the right, starting with A, since we have that printing out first. We do an SRA on A to fill its bit 7 with 0, and its bit 0 to the carry bit, which will now be clear. We continue by doing an RR on B, which will take that 0 from the carry bit and shift it into bit 7, and shift the 1 from bit 0 of B into the carry bit, which will now be set. We continue with an RR on C, which will have carry set, so 1 is shifted into bit 7 and carry is clear again. Finally, the HL variable will do the last shift, taking the 0 from the carry bit in bit 7 and shifting its clear bit 0 to the carry bit, which will again be clear. Now when we do bin regs, we'll see a 0 at the beginning, and then all the bits from the last line shifted one spot to the right, except for the last one, which is shifted out. Now we're going to OR B into A, so now A will have all of the bits that were set before, plus all of the bits that were set in B. Only bit 7 was clear in both, so that's all clear now in A. We print that out, then do an AND C, which will clear any bits in A that are clear in C. Now A is back to having only half of its bits set. We print that out again and do one more logical operation, this time an exclusive OR with the HL variable, which will flip all the bits in A that were set in the variable, which are currently bits 4 through 1. Let's print again and move on to some decimal rotation. First, we'll do a rotate left decimal, and we'll see the lower nibble of A move to the lower nibble of the HL variable, whose old value has now shifted to the upper nibble. The old upper nibble is now in the lower nibble of A. We'll print that out and then do a rotate right decimal, which will undo the left rotation and get A and the HL variable back to their old values. We'll print that out again just to see that it's gone back, and then try some bit addressing. We set bit 0 in A, then reset bit 1 in B, which will result in changes to both registers. So we print that out. Then we do a complement of A, which flips all the bits, and we print that out. Next we set the carry flag and start a loop where we do a rotate left on the C register. Print it out, then check the state of bit 4. We keep looping until bit 4 is set. Since bits 4 and 3 were clear at the start, it will take 2 iterations to get the set bit in position 2 up to position 4. Now that everything is printed out, we can set the colors of the text columns. It doesn't matter that we do this afterwards, as we'll only change the color attributes, not the pixels. We only care about the first 22 lines of text, as we wouldn't be printing more than that, and it will mean that everything we print will be on the screen at once. So we use B for a loop index, initialized to 22, then load the starting address of color attribute memory into HL. In each iteration, we load 0 into D and call the set color routine. This will set the ink color for the next 8 characters to the color value in D. 0 is black, so this will make the A column be all black. The set color routine will also advance HL as it writes out the color attributes, so now it should be at the B column. We increment D to make it 1 for blue and call set color again, which will make the B column blue. We keep doing this for the C and HL columns, which will be red and magenta respectively. Then we decrement B and keep looping until B gets down to 0 and 22 rows of this color pattern have been written. Now our program is done, so we restore the alternate HL and return to basic. All that's left to do is define the routines we called, starting with bin regs. We don't want this routine to change any register values or flags, so we use the stack to preserve them, first with a push AF to store the original accumulator and flag values. Then we call bin A, which will print the contents of A in binary. We start with the A column, so no need to load anything different there until we want to print out B in the next column. For that, we load B into A and call bin A again. A is still preserved on the stack, so no need to worry about overwriting it now. We do this again for C and the HL variable, then we restore A and the flags with a pop AF and return. Next we'll see how to do bin A, and for this one we need to also store BC on the stack, as we will be using both of those registers in this routine. We use B for a loop index, which we initialize to 8, as we have 8 binary digits to print. Then we start another loop with the bit loop label, but you may have noticed 2 things. 1, I already used the bit loop label before, and 2, in both cases the label names start with a dot. Well, this dot allows SJASM Plus to scope labels. Here I'm in the bin A scope, as that was the last label that didn't start with a dot. Before, we had a dot bit loop in the start scope, so they won't conflict with each other, and we can use a very generic label like that wherever we want, as long as it's unique in its own scope. Anyway, we start the iteration with an RLCA, which will rotate all the bits in A to the left, placing the value in bit 7 into both the carry flag and bit 0. Then we temporarily store that shifted value in A in the C register, as we need to use the accumulator to do some other things. The old bit 7 will still be in the carry flag, So we jump ahead to .print1 if it's set. Otherwise, we continue to load the 0 character, which is hex 30, into A, and jump ahead to .next. Then if we jump to .print1, we load the 1 character into A instead and continue on to .next, where we call the print character routine at hex address 10. Then we restore A by loading the value back from C and decrement to move on to the next bit. We keep looping until B goes down to 0, and we've done 8 RLCAs, which will effectively return A to its original value. Then we restore BC from the stack and return. Our last routine is set color, which needs to take an ink color in D and write it out to the next 8 memory addresses, starting with the current address in HL. For this, we use C as a loop index and initialize it to 8. Then in each iteration, we load the current color attribute value into A, and here we'll assume that the ink color is already 0 for black, which is the default for the spectrum. We OR the ink value in D, which will set it without affecting the rest of the bits in the color attribute, then write it back to memory with another load. We move on to the next character attribute by incrementing HL, then we decrement C to count down the bits. We keep looping until C gets down to 0, then we return. And that's it for the code. To generate a snapshot file that we can load in the Fuse emulator, we use the savesna macro and specify the file name bit.sna for the output and have it start executing at the start label. To do all this, we have a build script. We just call sjasm plus with the LST option to generate a machine code listing, and then pass it the name of our assembly file, bit.asm. Now let's go to the terminal and run it. We run build.sh, and then do a directory listing, and see that the bit.sna snapshot file is there. So let's load it into the emulator. We're using Fuse again, so we hit F3 and select bit.sna and let it run. And there's our header and all the lines of text we are expecting, including the colored columns. I highly recommend going back to the code and checking to see that the values predicted in the comments are actually printed out. Furthermore, you should try switching up some of the initial values and doing some more operations and printing the results. See if you can predict what the output will be. If you get it wrong, go back and review those instructions and see what you're missing. Bit-level operations can be very confusing, especially when you're starting out. But getting past this, we can move on to some even more interesting parts of the Z80 and the Spectrum. In the linked GitHub repo, you'll find not only this code, but all of the code examples for each lesson, and all of the slides presented in this series. In the README, you'll also find links to some additional materials that can help explain what's going on and provide some needed background in case your programming experience is a bit limited. Please subscribe to my channel and click the bell to be notified when the next episode comes out. And please like this video if you learned anything, and let YouTube know that you want to see more tutorials like this. If you can't wait for the next episode to go public, join our Patreon community and see my videos ad-free as soon as they are uploaded, just like the people you see here. Thanks for watching, and I hope to see you again soon. Bye-bye.